Hello everyone, in this video we are going to see about the concept of paging. Actually, we have it is one of the subtopic in memory management. So memory management is one of the main concept in operating system components. Okay, so here we have physical memory and the logical memory. When you have the physical memory, they are the frames. Okay, so physically, in the sense inside the computer memory, how the process and the data everything is stored, that is called as a physical memory, that is frames. And logically, a user thinks his program or a process has some logical units. Like for example, I am having a program having three subprograms, and I assume that I imagine that my subprogram function A is in one part of the area, a part of the memory area, and function 2 in the other part of the memory. That is called as a logical memory. That is the CPU. The user thinks, okay, the user thinks the way, that is called as a logical memory. So they are called as an blocks, and that blocks are of, they are called as an pages. So logically the blocks of memory is called as the pages, and physically how the system can store inside the memory is called as an frames. So we all know that the processes of bigger size and all the pages cannot be inside the frame, because the frame size is always fixed. Okay, so we cannot have all the programs inside the main program or the RAM memory to run the program. So every time we have to swap in the process between the main memory and the secondary memory. That is, we have to swap in the pages or the process between the pages and the frames. That is called as a mapping. Okay, so bringing the content from the logical memory to the physical memory for execution, and after execution we have to bring it back the pages to the logical memory, and so forth. This bringing back and forth the pages, the processes, components of the processes from pages to frame, that is called as a mapping. Okay, so as we know that CPU can access the physical memory, so now the system should always track of all about the free frames. Only if the free frames are available, we have also done some examples of the paging algorithms where always you have to look for the free frames. Only then the free frames are available, we can move the processes modules into the free frames. Okay, so as a conclusion, we can say that to run a program of n pages, we need to have n free frames and load the program. So suppose there are program is having n pages, that means logically there are n pages are there. There should be there should be n free frames. Then only those pages can be brought into the frames, and the process get executed. Okay, so in order to do this, there's mapping. In order to do the mapping between the logical memory and the physical memory, and back from physical memory to logical memory, we should have a translation scheme, that is called as an mapping. Okay, so here in case of this paging, we always come across the problem of internal fragmentation. What is internal fragmentation is, since the pages are all of the fixed size, okay, since the frames are all of the fixed size, what will happen? Once the process occupies the frames, some extra part in the frame will be left out without usage. That is called as internal fragmentation. For example, a frame is of 12K size and a process of 10K size comes in. The process fits into the frame, so remaining 2K is wasted. That is called as an internal fragmentation. Okay, so now let us see this architecture, address translation architecture. So why it is needed? In order to translate the CPU, which is the logical memory, to the physical memory, which is the frames. So this is the pages and this is the frames. Okay, so we have to convert from the pages to the frames. In order to do that, we have this arrangement. This is the architecture, and let us see this architecture here. So P is the page size, and then D is the offset. That means how many pages the process can be handled. That is called as an offset. Okay, and then likewise here after this, so the pages are stored in the page table, and here you can see here in the pages frames are set. Okay, and then we have some two indicators V and I. V is valid, I is invalid. So if it is an invalid bit, the system cannot, that means the page is not available in the page table. If it is invalid, means it is already being removed for some reason, so we have to bring it back. So if it is V means valid, the system can access the pages. Okay, so only the valid pages are translated into the physical memory, which is the frame memory. So we are getting the frame address with the offset. So we can conclude here, from the pages it is converted to frames. Okay, so while doing this conversion from logical to physical memory, the address translation takes place like this, so that the data are stored. This is the addresses in which the memory blocks are stored of the blocks of the memory process memory are stored in the physical memory. This is how the translation takes place between the logical and the physical memory. And then an example is given over here. You can see this is the logical memory, this is the physical memory. So now here, from the logical memory, each block is of 4 size, 1, 2, 3 and 4. Okay, so how this mapping is done, this is just similar to the previous diagram. CPU, page table, physical. Same way here, CPU, that is logical memory, page table, physical. Okay, so let us see this conversion, how it takes place. Now here in the page table, we can see here the 0th block is stored in the 5th position of the page table. Now we know that every logical memory has a block of 4. So then now in the physical memory, where it will be stored is 5 into 4. So this is the plus 0, that is 20. So 5 into 4 plus 0 is 20. That means it will be, the 0th block will be stored in the 20th position. That means you can see here it comes to the 20th position. So 20 has A, and then 21 is B, 22 is C, and 23 is D. So the mapping took place between the logical and the physical memory. Same way, you just take the other example of this 3 and then 2. That means the third block, this is 0, 1, 2, the third block. In the third block, it is stored in the page table in the second address. Okay, so what is the second address? You can see here, this is M. Okay, so now here this is the 12th position in the logical memory. Okay, now this M is placed in the 8th position. How it is in the 8th position? This is the second location, and it has the 4 as the size. So 2 into 4 is 8. So 2 into 4 is 8 means this particular value M, which is stored in the 8th position of the physical table. Then naturally 9 comes in the 9th position, and 0 comes in the 10th position, and P comes in the 11th position. Okay, so this is how the mapping takes place between the logical memory and the physical memory. And now you can see the free frames. So the free frames are always checked to make the paging from logical to the physical memory. So we can see here initially this is the free frame list, all 14, 13, everything is free. And now this is the scenario, a new process comes. So page 0, 1, 2, so 4 pages are coming as in the new process. So naturally it will occupy the free frames. Okay, so 13 is given to, so it is given as randomly. So 13, 14 and 18 and then 20. So these blocks are occupied based upon some algorithm. So we can see here page 1 is given the 13th address, then page 0 is occupied to the 14th address, and then page 2 is given the 18 address, and then page 3 is given the 20 address. Out of this you can see here, because it's the last frame to see, this is actually not occupied because 4 processes came, 4 free frames allotted, so 15 is left out. So now in the next scenario, there is when the new process table comes, this is the scenario, the free frame is only 15, and now this the new process has come. In the new process, this is the page table, so 0 should be stored in the 14th page. So after this allocation takes place from the free frames from the new page arrival, new process arrival, naturally the page table changes. How it changes? 0 is holding 14, and 1 is held in the 13th position, and 2 is held in the 18th position, and 20 is held in the page 3. 20 is occupied by the page 3. So that's all how the free frames are occupied from the process allocation technique. So hope this will, you have understood the concept of how the paging takes place and how the mapping between the logical and the physical memory take place, and thanks for watching.